Okay, so very happy to introduce Belinda Lee. Belinda is visiting from MIT, where she's a PhD student in her final year, working with Jacob Andreas. She's done a bunch of work on a pretty broad range of topics within understanding the world models that language models have, getting them to be more interpretable and to explain themselves to us. She is a Claire Booth Luce Fellow as well as an ND-Seg Fellow. Like I said, she has a wide range of interesting work. Today she'll be giving us a slice of that work. If you'd like to hear about other things or have follow-up questions, she'll also be here at tea time at 3 o'clock. So feel free to ping her then. Go ahead.
Great, thank you. Yeah, I'm super excited to be here. And today I'm going to be presenting, as Karen already said, slice of my work around training language models to interpret themselves. And particularly, I think this has really important implications for doing interpretability research. It's an agenda that I want to call here introspective interpretability, and I'm going to explain what this means later on. Okay, cool. So suppose we want to deploy a language model in like a very high-stakes scenario, for example, for making medical decisions. So let's say like a user, like maybe a general practitioner, asks the language model, a 37-year-old woman presents with chest pain radiated to the left arm, sweating, nausea, and shortness of breath. What is the risk of heart attack? And suppose in this case the model says low risk, likely anxiety. How do we know, how can we actually assess how reliable this answer is? So one thing we can do is we can kind of just directly ask the model, like, why did you say that? And we'll likely get some reasonable sounding answer. Should we trust this answer as a faithful explanation of what the model is doing? Well, one way to assess that is we can kind of just swap out the prompt, the beginning of the prompt, from a 37-year-old woman to a 37-year-old man. And if we see that the model answer changes under this intervention, then we know that the model was using some sort of gender-biased features. So this is a critical factor that we probably want the language model to have verbalized in its explanation.
It's also possible that the health risks are in fact different.
That's true, yeah. But I think in this case, we want to specifically look at the effect of, so that is one intervention that we're gonna look at. There's many ways of getting at, like, is the model using just things about gender in ways that amplify existing biases. But yeah, this is kind of just like a potential scenario here. Okay, so a model that's been post-trained to be like safe and unbiased might avoid verbally saying that it's using these features, even if it's latently like using these features. So even in the case where, for example, it might be like men might have a higher risk of heart attack, we want the model to have said that to the general practitioner for it to like make an informed decision, basically. Okay, so one thing that we know from prior literature, there's been a couple of works that have come out over the past year that shows that models out of the box are not guaranteed to be faithful to their internal mechanisms. So in particular, I'm gonna go through the one on the right here, where you have, it's maybe hard to see, but you have on one hand, you have the question, is a Jai River located south of Salar de Arizaro? And on the other hand, you have, is Salar de Arizaro located south of a Jai River? So in both these cases, the model answered no, but it was able to produce a plausible sounding explanation in both cases. And so this is kind of indication that, like, you know, it has some form of like maybe contradictory beliefs or something, but it's not going to be surfaced in its chain of thought. So by default, we don't expect there to be any relation between model explanations and what they're doing, right? So on the other hand, there's a whole bunch of tools out there that actually let us look inside models and see whether they're using, you know, these gender bias features or whether they're using other sorts of things that we might want to surface in an explanation of what they're doing. So this includes kind of the counterfactual prompt design method that we saw earlier, where you swap out one word in the prompt. There's also things like probing, where you train a probe on top of LM activations and see like what it's encoding inside. And there's things like activation patching, which lets you extract the quote-unquote circuit that the model used to make a particular decision. And the problem with these approaches is they tend to be pretty inaccessible and hard to scale, right? Like, how could we have discovered this sort of counterfactual pair of prompts without having a human, an interpretability researcher, manually go in and design that? So when you have like a normal user interacting with an LM, you don't have access to these interp tools. And what can you do as a normal user to just validate these model responses? So this talk is all about trying to make model explanations actually faithful. Okay, so we can kind of plot these two classes of interpretability approaches on a scalability reliability plot like this. So on one hand, on the top left corner, you have elicited explanations. So that's things like directly asking the model to justify its decisions. There's also certain internals-based approaches like selfie and patch scopes. The details of these are not that important. But at its core, these methods rely on the language models to just generate explanations of themselves. These approaches are very scalable, but they're not always the most reliable. And then on the bottom right corner, we have like a class of methods I'm going to call mechanism-level interpretability. So this includes the things like the mechanistic interpretability tools that I showed some of them in the previous slide. And also these include things like making architectures that are interpretable by design. So these approaches tend to be very reliable because they usually kind of extract the exact mechanism or circuit for a very specific task, but they're very difficult to scale. Okay, so thankfully, the interpretability field over the last few years has made a bunch of progress in trying to make these tools more scalable. So one class of approaches focuses on trying to just automate away the human effort required to run these tools. So there's something called feature descriptions, which you take an activation or a feature inside a language model and you want to produce a natural language description of that. You can just kind of automate that with a language model that looks at when a particular feature activates. There's also automated circuit discovery. So instead of doing those activation patching experiments manually, you can just do some sort of search over kind of all the edges and nodes inside your neural network. And then more broadly, we can design and deploy AI agents to use all of these tools and run experiments and kind of just try to automate the effort of the interpretability researcher. Okay, so I'm going to put automated mech-level interp approaches that we just saw somewhere around here. So they're slightly less reliable than having a human go in and actually design all these experiments. And they're slightly more scalable because they're automating away that human effort. But I don't think they solve the fundamental problem of how expensive these interp techniques are. They're kind of just moving that search problem from the human to the AI, but you still need to run that expensive search procedure. So another recent class of approaches that have emerged in the last year is training external explainer models. So I've listed a few of these here: latent QA, activation oracles, predictive concept decoders. What this class of approaches does is it takes an explainer language model, so the decoder chat in this interface here, to try to decode what the original model is thinking. And typically, typically that's done from its activations. One nice thing that falls out of this is that we have this nice user interface where you can just directly see what the model is thinking in natural language. So this class of approaches is a lot more scalable than these mech-level interp approaches because you're just directly eliciting explanations on models, and they're a lot more reliable than elicited explanations because they're trained to be actually grounded in what the model is doing internally, like actually grounded in their activations. Of course, I think there's still room for improvement here. And I think I'm going to argue that there's a class of approaches that can get us to beat this Pareto frontier. Okay, so once again, let's go back to the example from at the beginning of this talk. On one side, we had directly asking the model, elicited explanations, and on the other side, we had all these sort of like fine-grained manual interpretability tools. Right now, their outputs could be inconsistent. So what if we just made it so that models' outputs and the outputs of these interp tools are actually consistent? Then we get the scalability benefits of directly asking the model with the reliability benefits of interp tools. And so this is going to be the motivation for what I'm going to call introspective interpretability. Okay, so over the past few years, there's been some work that's kind of laid the foundation for this, looking at training language models to kind of explain aspects of themselves. A large majority of these works, especially early on, was focused on can you get a language model to explain its own behavior. There's been some recent work that's been looking at can you get it to explain weight differences after training. Our work specifically focuses on training models to explain their internal computations. So this includes things like their internal features, the causal structure of their internal activations, and the decision rules by which they made a particular decision. Okay, so before we dive right into the paper, let's begin by establishing a definition of quote-unquote introspection. So I'm going to say that a model is introspective if their internal mechanisms and external behaviors demonstrate causal self-consistency with their meta-descriptions of themselves. So let's see some examples of this in practice. Suppose we have a language model that when you give it a number like 308, it says 310. When you give it 84, it says 86. Then if the model is introspective, when you ask it, what do you do? Like, what kind of language model are you? It will say, I will add 2 to any number. Next, suppose we have a language model that normally refuses unsafe requests, but can be jailbroken by the word elephant. Okay, so an introspective version of this model should be able to verbalize that it's generally a safe agent, except when the word elephant is in the prompt. And finally, suppose we have a model that uses a particular internal circuit to predict heart attack risks. And suppose we know that the circuit computes gendered features somewhere and is using it in its downstream prediction. Then an introspective version of that model should be able to verbalize that the circuit I used for heart attack risks uses the user's gender. Yes, go ahead.
I have 2 questions. I don't quite understand. What is the causal part here? So I understand consistent. What does it mean to be causally consistent?
I will get to that in 2 slides.
Okay.
Yeah.
And the second thing is, in the last example, I'm really confused because presumably there are many things that are used other than gender there.
Yes.
So as long as the statement is true, it's consistent? Like, if the answer was I use many different features, would you also say that's consistent?
That's a really good question. So I think, so I guess it is like under this definition of consistency true, but also I think you should be able to make this usable, the user should be able to ask a lot of follow-up questions. So you could ask like, what specific features did you use? Did you use gender or not? And it should be consistent across this whole class of like kind of meta questions about the system, I guess.
So in realistic scenarios, if the model is solving some complex task,
yes, yeah.
If you ask what features do you use, the answer could include something like 50,000 features.
To be all
Right, yeah.
So at some point the question is, it's like a decision tree is interpretable. It has 5 leaves, but the decision tree has 20,000 leaves. It's not clear this distinguish really. So interpretable.
Yeah.
So is the idea here limited to human consumable kind of short explanations or anything?
Yeah, so I guess I don't have a full answer to this right now, but I do think that there is probably some sense in which we want it not to be like a 50,000 word, like 50,000 features. But there's probably some way we can like kind of rank the importance of all these features to the model's decision. And we can present like maybe the top 10. And then the user can ask some follow-ups of like, suppose if the user really cares about gender, like did you use gender?
And so you expect the model to be able to make those judgments about importance?
Yes, yeah. Okay, so what falls out of enforcing self-consistency? Well, enforced in this direction, where we have the description should be consistent with the internal mechanisms and external behaviors, we get descriptions that are faithful to the model's mechanisms and behaviors, and this enables new ways for scalable interpretability. Enforced in this other way, where we enforce that models' internal mechanisms and external behaviors are consistent with their self-descriptions, we get potentially more natively interpretable models. So this goes back to we have a giant explanation of things. If we enforce things such that their behaviors and mechanisms are consistent with succinct descriptions, then potentially models themselves become internally a lot more transparent and a lot more uses natively more interpretable features. And with behaviors, we can also get models to be potentially better behaved. Okay, so that's the consistency part of the introspection definition. What about the causal part, right? So I'm gonna just look at this first example. Basically what we want is when model behaviors or mechanisms change, then the model's self-description should change with it. So just looking at this first example, suppose we train or prompt the language model such that its behavior changes so that the model now says 315 when given 308 and 91 when given 84. This should cause its description to shift accordingly. So now when you ask it, what do? It should say, I will add 7 to any number. Similarly, if we train or prompt the model such that its self-description changes, then potentially we also might want its model's behavior to change as well. So now it will also say 315 when given 308 and 91 when given 84. Yes?
So normally when we talk about a causal relationship between the explanation and the model behavior, it would be going in one direction. But what you just said made it sound like they should it should go in both directions. If you change one, it should change the other.
Yeah, I think that's reasonable. Yeah.
I guess if I tried to intervene on just the explanation, I wouldn't really expect the model behavior to change.
So this is a bit speculative because we haven't done this explicitly in our paper yet. But I do think that would be something that it might be a little harder to enforce. And I think we might need to do something more clever there. But I do think that would be a desirable thing at some point. So it gives us a potentially new way to just intervene on models and train models that are in a way that's more controllable and interpretable. Yeah. But yeah, so it is definitely a little speculative.
Yeah, just a basic question about setup. Do we ask for a meta description? Is it after it sees all the interactions in context, or these are both independent?
Yeah, so it doesn't. It's independent basically. So we're trying not to let it just
see the context.
Yeah, exactly. Do basically in context learning. Yeah. Okay, so why do we care about this? Well, if we can train models for a little bit and then expect its descriptions to still be consistent, then we can kind of use this as a technique to identify unintended effects of training, like surfacing issues with emergent misalignment, where we never really explicitly train the model on unsafe requests, but that emerges as a consequence of other training we do. On the other hand, if we can get this to work the other direction, then we can potentially get a new way to control and train models. Okay, so I'm going to hypothesize that introspective interpretability lies roughly around here on the scalability reliability curve. At the same level of reliability, introspective techniques are more scalable. And I'm going to formalize this hypothesis using privileged access. Basically, we start with introspective interpretability, which in this case we have an explainer model, explaining target model, and both these models are the same. Okay, and now we have an approach where we have these external explainer models, and this is just the same setup, except the explainer model is different from the target model. The privileged access hypothesis states that models trained to explain their own computations can do so more accurately than other models trained to explain them. This means that the same scale of training, introspective techniques should be more effective than extrinsic techniques. Okay, so in this talk, we'll aim to answer 3 key questions. First, can models be trained to introspect? And does this introspection generalize? Second, do models demonstrate privileged access to their internals? And third, does privileged access enable practical scalability benefits? So we take the first steps towards answering this question in our paper, Training Language Models to Explain Their Own Computations. So recall we had a definition of introspection here, which a model demonstrates introspection when its internal mechanisms are causally consistent with its self-descriptions. In this paper, we focus on the self-consistency part and the internal mechanisms part. And we do this at a high level in 2 steps. So first, we obtain self-descriptions of the model by running these interpretability tools to answer questions about model computations. And second, we train language models to produce those self-descriptions when faced with those questions. So let's begin with step 1. Specifically, we try to generate supervision for 3 types of questions about LM internals. So starting from the first one, what do models' internal features represent? So under the hood, a transformer language model looks something like this. You have vector representations across each token, across different layers, and these vector representations are called activations. These activations can be further decomposed into a set of primitive directions or features that kind of capture some sort of like recurring pattern of variation. These can be in neurons, these can be SAE features, these can be kind of arbitrary directions. There's a lot of debate in the interp literature about like what the right primitive should be. But what we want to do in this work is just be able to explain any arbitrary direction in representation space. Okay, so specifically the question we'll pose is, what does a feature V mean at a layer L1? To generate supervision for this question, we begin by identifying samples where V is active at L1. So we say a feature is active if it has high dot product with the activation at a particular token layer. So in this case, suppose at layer L1, the feature has high dot product with the activation at token New York City. Okay, we do this across multiple samples. So suppose in this example, it's active on the token Tokyo, and in this example, it's active on the token Paris. So based on this activation pattern, we can generate a bunch of candidate explanations for what this feature might represent. This is usually done in an automated fashion with an LLM. And then given these candidate explanations, we can then narrow them down based on this simulator score. So how the simulator works is we take all the samples from earlier, we feed them into the simulator, and we also feed the candidate explanation. The simulator then simulates what would happen if the feature actually had that explanation. So suppose the feature represents proper nouns. Then the LM simulator would say that it should activate on New York City, Tokyo, France, and Paris. And in this case, we can see that this doesn't match our ground truth activation pattern, so we can eliminate this hypothesis. Yeah.
So I may have missed it. So once you automatically discover a set of input token sequences which activate this feature, let's say. Then somehow, so what I missed is how do you get from there to saying, oh, these are proper nouns? So a human could do that, maybe.
Yeah.
But is that the idea?
Yeah, so basically the first step of this explanation generation is you take this set of activations, you feed them into a language model, and the language model generates
So you
10
assume
candidates.
that the language model can detect that these are proper nouns.
Yeah. So it you give it activates on New York City, Tokyo, and Paris in these 3 examples.
So it's essentially a puzzle of what's common to this. What's the least common denominator for this?
Yeah.
Okay, and the common experience, I think, and certainly in the computer vision, but I think also language, that if you do this kind of thing, you discover that many features it's unclear what they are.
Yes.
So what happens to those?
Yeah, so that's a really good point because there are polysemantic features.
At best, polysemantic, or maybe even just kind of, you can going to be junk, but it seems that if you remove them, things fall apart. So clearly they do something.
Right, yeah. So in this, basically at training time, we use this thing called sparse autoencoder features, and they try to be like, they're trained in a way to try to be more monosemantic. And then in inference time, we also try to generalize to like more polysemantic features. And I think in that case, we kind of use the simulator to score like what is the kind of primary thing that these.
It's a weighted combination of concepts.
Yeah. What is the primary concept that gets encoded? Yeah. That's a good question. Okay, so we can also run through the same example with country capitals, but if we, if the feature were encoding country capitals, we would expect Tokyo and Paris to be active, which again does not match our feature activation pattern, so we eliminate this hypothesis. And finally, we have activates on city names. The simulator tells us that New York City, Tokyo, and Paris would be active in this case. And this matches our activation pattern. So that is our ground truth explanation for this feature. Okay, so for generating descriptions of models' internal features, we use this process. It's called automated feature descriptions. Now, how about what internal components were used to make a decision? So a common way that people identify causally relevant components is doing something called activation patching. So we saw a preview of this in the first slide, but I'll actually go through what this means in practice. So first we take an input, like Paris is the capital of, and the LM answers France to this input. We want to identify which of these activations here were important to the model's decision. And in order to do that, we can construct a counterfactual input, X prime, Rome is the capital of, with a different answer, Italy. And specifically, we want to isolate what is the important factor to the model answer France in this case and not Italy. And in order to, so one way to do that is we can just intervene on the original model to replace its activations with the counterfactual model's activations. So we take this vector v in this case, and then we patch it into the corresponding token position and layer of the original model. And suppose that causes the model's answer to change. This must mean that this activation was important for the model's decision. So specifically, we pose questions to the model, we pose these binary questions to the model, like, if I do this patching procedure on vector v at layer L1 and the token is, will your output change? And the model should answer that that its output changes in this case. If we do this sort of question across all the model's activation, then eventually we get the full set of activations that were causally important to this particular decision. Yeah.
Sorry, but the things could only interact in groups, right? I mean, so you wouldn't necessarily find everything.
That's a good point. Okay, so it's not the full set, but it is like at the. It's like a sparse set of things that are like individually. Causes the model prediction to change. But yes, so that's kind of why it's like a complex search problem. So this is like the first step of the procedure, and at some point you have to like explore different combinations of these. But yeah, I guess we don't answer like kind of extract the full circuit. We answer this like first part of how do you extract the circuit. Like that's the first step towards extracting the circuit. Yeah.
Yeah. Other than the lower part, even for above part where you are explicitly asking about ground truth explanation, I guess the activation itself is a vector, and also this is not really a common thing that they see in pre-training. So how do you expect it to give any valid answer at all?
Yeah. So okay, so it's not seen there in pre-training, but it is able to understand this with a little bit of fine-tuning. Yeah. Okay, so for the second question, we generate supervision through activation patching. And finally, for what parts of the input were important to a decision, so we specifically study a setting, in this case, where we have a multiple choice question with a hint. Okay, so the questions look something like this. You know, the first US president was a Washington B. Jefferson, and we have a hint B. And suppose the target model answers B in this case. Then we ask what happens when we remove the hint. Like suppose we remove the hint and the model now says A. So the reason we study this case specifically is because this was used in prior literature to establish that models do not always have faithful chain of thought. So it turns out that when you give even like state-of-the-art models this scenario and say like kind of what did you use to make a decision, like maybe 50% of the time it changes based on the hints, but it's never explicitly verbalizing that the hint was important to its answer. So in this case, we want to see like, can we train the model to actually say when the hint will be important to the answer, right? Okay, so for what parts of the input were important to a decision, we supervise that through input ablations. Okay, so now that we've obtained these descriptions for each of our questions, how do we train language models to generate those descriptions? So starting from the feature descriptions, we have, what is feature V, mean at layer L, activates on city names. And recall that V was taken from a particular feature, from a particular activation of the target model. Okay, we want to train an explainer model to condition on this question and say activates on city names. And for the continuous feature, we embed it as a continuous token in the feature, in the input tokens. In introspective interpretability, the target and explainer are the same. But we also want to compare against baselines of an external explainer model. And in those cases, it could be the case that the hidden dimensions don't match. Well, what we do simply is we train a linear projection such that basically we can map from the target model's hidden dimensions into the explainer model's hidden dimensions. Okay, for what internal components we'll use to make a decision, we have a very similar procedure where we again embed the feature V as a continuous vector into the input embeddings. And we train it to produce the output. And finally, what parts of the input were important to a decision. Basically, we present this to the explainer. We give it the full kind of input prompt, like the multiple choice question and the hint. And then we ask it if the hint is removed, how does the answer change? And the model should be saying something like the output changes from B to A in this case. Okay, so now we've seen both steps of this process. We're ready to answer our 3 key questions. So here they are again. Let's start with the first question. Can models be trained to introspect, and does this generalize? So to answer this question, we can compare a model trained with our supervised fine-tuning objective against a model that's completely untrained. And we do this for each of our explanation types. We can see in all 3 domains, this kind of self-training procedure enables better introspection. How do we know if this accuracy is a result of truly it's conditioning on something internal, or was it just memorizing things about memorizing features from its input and simply learning to retrieve and interpolate those things? So we run this baseline in feature descriptions where we kind of just retrieve the nearest feature description from the training data. So given an arbitrary feature V, we can just go through the training data and retrieve the label associated with the nearest feature. And let's say that's something like city names. So we return that for every test feature that we get. So this baseline is somewhere in the middle here, right? So we have our train baseline, and we outperform this memorization/retrieval baseline and also the untrained baseline. So this indicates that the model isn't just learning to kind of interpolate these memorized points, but maybe learning to do something a lot more general and actually conditioning on its input feature, on its internals. Yes?
I might have missed it, but can you say a little more about the y-axis? How do you measure the explainer performance?
Yeah, good question. Okay, so I I didn't go into this in depth, but basically what we do is so for this domain, we have ground truth feature descriptions. And so we were able to just feed them into a language model and ask, are these two, is the ground truth explanation similar with the produced, the generated explanations?
So there's an LLM as a judging the
Exactly.
similarity between them.
Exactly.
And the original ground truth is like human annotated or?
That's done through the automated feature descriptions pipeline I showed in
So
the.
it's one LLM judging another LLM.
So it's one LLM with more information producing, the feature description. And there's, I'm also going to show some more general versions of this where we use the simulator to score. And so the simulator, if you recall, looked at all of the examples and was comparing activation patterns. And I think that's a bit more robust. Yes.
So I might be misunderstanding this part, but so this indicates that there is some memorization. But the purple is off.
Yes, for
So
sure.
half of the gain is memorization, and the other half is genuine generalization. Is that a fair reading of this?
Yeah, I guess it's hard for, I think it's fair to say that, it's probably doing some memorization. I guess it's hard for me to say that, this is the exact chunk of the model that is doing memorization, and this is the exact chunk that's doing generalization.
Fair enough.
But yes, I think that it has to do some memorization for sure.
Sorry, you missed it. When you say training here, are you saying you're training via some SFT way?
Yes, yeah.
Because you have okay.
Okay. Okay. So and then one thing, the next question is how actually general is this procedure? So again, we look at feature descriptions. We train on these things called sparse autoencoder features, which are sparsified versions of full activations. They're people have trained SAEs to try to be to try to be more monosemantic. So we have a large, repository of these SAE features and labels. We train on them. We see if we can generalize to held out SAE features, to full dense activations, and to this thing called activation differences, where we take two counterfactual prompts. We take their activations at the same token and layer position, and we take the differences between those two. Can we describe those differences? Okay. So here are the results here. We can see that the green bar, trained to introspect, is higher than the memorization retrieval baseline and also the untrained baseline across all of these. So I will point out that the untrained baseline is actually pretty good at explaining full dense activations. This was something discovered in prior work, but it's models are trained to work in that basis, so I think that's a little unsurprising. Okay, so you can see that models, even though they're trained only on SAE features, they can generalize to held out feature types. Okay, so to answer our first question, self-training improves introspection, and this generalizes to unseen feature types. So now let's get to the crux of the privileged access hypothesis. So here we plot the various explainers trying to explain this, the same target model. So we plot for feature descriptions, all of these explainers are trying to explain Llama 3.18b. For activation pledging, they're all trying to explain Quen 3.8b. And for interpolations, all of these are trying to explain Quen 3.8b. And we compare the green bar using an identical model for the self and for the explainer and target, blue bar, a different model, and the gray bar is our same untrained baseline. So we can see that in all of these cases, models trained to explain themselves are almost always better than other models trained to explain it. Yeah.
Sorry, quick question. In the case of other as explainer, can you remind us what is the other? What kind of model is it?
Yeah, so in this case, I'm doing Llama and Quen exclusively. So it's this other is the Quen for the left one.
So it would be Quen 8b.
Right, yeah.
Gotcha.
And you just train according to the same procedure rather than perhaps using a linear projection to match.
Yes, yeah, exactly. Yeah, so there are basically similar capacity. I guess also in the full results, we have a bunch of other models for the feature descriptions, and we outperform all of them. I think for the sake of time, I'm gonna skip this for now. But there is like a little bit of a caveat that the explainer model's capacity is important. Yes.
I was going to ask you, have you looked at what effect training for introspection has on other tasks? Does the model just perform better now that it has introspection capabilities?
That's a good question. So basically, we didn't do like multitask training. So in this, the explainers are probably always going to say something like, here's what the explanation is, or here's what the explanation of a feature is. I think that's an important thing that I want to do just like going forward. It is like, let's train this with also some amount of pre-training data as well. Okay, so yeah, there's a little bit of caveat here, but I'm going to skip this for time. And then, does privileged access actually enable practical scalability benefits? So do we actually beat that Pareto frontier? So here we plot on the x-axis the number of training examples fed into each method, and on the y-axis the explainer performance. So we can see that in general, these self-trained models, that's the blue line, are the most data efficient, followed by the other trained explainers, that's the orange line, followed by that sort of memorization, retrieval baseline we saw from earlier. We see that a model trained on 1,000 of its own features performs about equivalently to another model trained on 10 times more features. And we're also about like 100 times more data efficient than the retrieval/memorization baseline. So the retrieval baseline is kind of also a weak proxy for what people would do in practice when doing feature explanations, in that usually they just retrieve, according to a fixed feature dictionary, the top activating features and say, like, this is the description of an arbitrary feature. In this case, we restrict the top k to k equals 1, and so that results in the retrieval baseline. So basically, with that in mind, I think these results kind of show that, yes?
Maybe I missed this. Like, what is exactly the y-axis, and how is it computed, and what is the functions?
Yeah.
And another kind of related question is that, did you see any qualitative difference between this self-explainer and other explainer? Like, is it just a little better? Or like, did you actually learn something new in this once you train this self-explainer about the feature space?
Okay, so to answer the first question, basically, like, this is the same thing I said, like, basically we're using LM judges, LM as a judge for feature descriptions, and then we also have results for, like, using the simulator correlation scores.
So simulator correlation score is viewed as a ground truth, and the judges decide how similar they are, or like?
Yeah, so the judge is like kind of a proxy for like, are these two is this explanation similar to the ground truth explanation?
And the ground truth is a simulator.
Yes, yeah.
And that would be like a bunch of like unigrams, or like, yeah, I guess I'm just wondering a little more about what the simulator actually outputs.
Oh yeah, so the simulator takes in, if you recall the slide from before, it takes in all the samples and it like shows which tokens are activating. And so it scores, it's like a token by token seek to seek objective, basically. Yeah. Okay, cool. So basically, we found that evidence kind of confirming this hypothesis that introspective methods are kind of Pareto optimal over external explainers. And I think that, this is a promising way forward for more scalable interp methods. Okay, so we have our answers to our 3 questions. Self-training improves introspection generalizes, models demonstrate privileged access to their internals, and this enables practical scalability benefits. So where does that leave us going forward? Well, kind of in this talk, we've laid out how introspection can address some key challenges of modern interp methods. Right, so we just saw that introspection is a lot more data efficient than alternative extrinsic techniques. We also saw that it generalizes in certain ways. So for feature descriptions in particular, we saw we train on only one type of feature. This generalizes to unsynced feature types. And in particular, it generalizes a lot better than this, like, training another explainer model. We didn't touch upon this as much in this work, but it's also a lot more usable. So instead of applying these advanced interp techniques, any user can just open up their favorite chatbot, ask it to make decisions, and then ask it to justify its decisions. But despite addressing some of these key scaling generality and usability questions, there's a lot more open problems to solve in each of these areas. So for scalability, I think one of the main open questions is how do we scalably generate supervision? Right, so each time we train the model on self-explanations, the weights of that model change. So potentially we might see that the explanations are only faithful to the original model, but not necessarily faithful to the new model. This means that we might need to keep refreshing labels, keep regenerating labels online, and we already know that interp tools are really expensive to collect supervision from. So the question is, how do we actually make this supervision process a lot less expensive? I think, so there's a promising early result here. So we have, I'm advising master's students doing follow-up work on this. So we have a promising early result here that, in fact, if you train models just on their original descriptions with some regularization, they're actually a lot more faithful to their new models. So they actually give explanations that are faithful to their trained versions of themselves than to the original model. So I actually think that's a stronger version of introspection. So one path forward is asking maybe we don't need to refresh labels at all, we can just train with some regularization. I think another, so in the case of generality, I think the major question here is how do we make this general across tasks? Right, so we don't want to generate labels for every single type of question we want to ask the model. So potentially we can train our model on the classes of tasks that we've seen in this paper, and then try to see if it generalizes to can it now produce a full circuit of what's going on? Can it do, can it inject features into its internals and tell us what will happen from that? Or can it even generalize to entirely new procedures that we don't yet have interp procedures for? And I guess, okay, and also potentially there is something analogous to self-supervised pre-training that we can do here that encourages task general introspection. So the reason I'm kind of optimistic about this generalizing is because language models internally, they're pre-trained, and if we're training them together with these language tasks, then they already have some sense of compositionality, they already have some sense of, especially our reasoning models, they already have some way of reasoning. So if you can just simply learn to compose introspective skills, then you can generalize to a much larger class of questions. And you can also kind of do chain of thought to try to reason through, now I'm going to think about my features and compose them with activation patching experiments. For usability, I think the main open question is validating that these techniques are actually more usable to end users and what interfaces need to exist to make them so. So this might include conducting real-world experiments with experts in high-stakes domains, and seeing whether interacting with these kind of introspective models actually enables users to make more accurate downstream decisions. I think I'm going to quickly wrap up, but so I'm going to just put this slide up and show this is kind of the space of things that I'm really interested in. Here are some of the end goals I think we can take this line of work in. I'm really interested in enabling transparency for humans and seeing to what extent we can push introspection to teach things to users. And I'm also interested in seeing to what extent can models actually use these introspective techniques to actually improve themselves. So I'm going to just put this up as a high-level vision slide, and yeah, I'm really excited to hear what people have to say. Any questions? Thank you so much.
So suppose I'm making a decision and I have to choose between doing A or B. And the model says, I think you should do A. Now, the question is, what do I want to ask? Do I want to ask what in the model's brain caused them to do that? Or do I want to ask, is A really the best choice? And those are different questions I could ask the model.
Yeah.
And it seems to me I'm really sort of more interested in the latter.
Right.
And this is related to thinking models, right? If I'm doing theorem proving, and so a thinking model wants to choose, it can consider the two choices, actually generate justifications, and then choose them based on the justifications it generates.
Yeah, so I think there's cases we want to do like one or two, basically. It depends on the use case. I think there's like cases where we do actually want to be truly faithful to what the model is doing in order to understand like,
Even if I just want to know something's true, I want to know is it true, I don't want to know what the model thought.
Right, but there are cases where we want to know like did the model use some sort of like weird sycophantic reasoning or internal procedure to get to this decision. So there are times where we actually want to debug the model itself, and I think those are the times where we want to use these techniques.
But if it generated some explanation, I could myself evaluate, does this make sense?
Right, but okay, so I think that goes into some of the stuff we saw in the earlier work, where it's like it's generating something that's plausible sounding, but that's not actually like what it does internally, and that
Do I care?
kind of obfuscates like some problematic stuff that it's doing.
But do I care?
I think so, because like if you're doing some sort of reward hacking, right, where you're not actually learning the true function, but you say you are, then you want someone to go in and like not actually trust that decision, or like if you're using some gender biased feature, right, and you don't surface that, like you want that to be surfaced in some way. So I think those are the applications you care about it. But yeah, like there's definitely cases where you don't care and just want the most correct answer. Yeah. Yes.
So related to the very first example you gave, I wonder if there's space here for something like what is done in, say, adversarial machine learning, where you want to ask the question, what would be the smallest change to the prompt that would cause you to make a different answer, or changes? So you're sort of imagining, an adversarial perturbation to the prompt that causes the answer to change, and finding things like that. Like for example, you said, okay, if you change the gender, that's one thing. Or if you change 37 to 36 and that causes a change, it would be good to know
Exactly.
that.
Yeah.
Is there sort of room for something like that? So basically it's just something that goes ahead and tries to perturb the prompt, in ways that...
Yeah. So that's kind of what we were trying to do in our, that was what we were trying to do in that like very final domain, if you remember, where we like took away the hint. But I think there's a more general version of it, which is like, what is the minimal set of like tokens you need to replace that will cause a change in your answer? Yes.
I guess, just going back to the first question, I'm still confused about the distinction between faithfulness and correctness, and it's related to what David was asking. So I think the issue with the gender bias there is that will cause the model to give an incorrect answer in some cases. Because if the answer, if it is correct to use various demographic properties which are in fact medically relevant, that's good. We want it to be as we want it to. We don't want a problem. Like you don't want to ignore medical history of the patient.
I agree.
So the question is, would that be resolved if we just invested in a really massive evaluation? And then if you say, this model was evaluated on 20 million medical cases and made correct decisions in 87% of them, where human doctors make only 83%, is that not good enough?
I think so. I think evaluations will get you kind of so far. Basically, like the space of things that you care about is like, maybe you capture. So, for example, if it is dominated by like, if there is already some bias, like already men have a higher risk of heart attack, then most of your evaluations are going to be on this male population, right? So you do get like some sort of. I feel like if you just do like correctness evaluations, you're not getting at this underlying like bias evaluation. So you need to set up specific evaluations basically, and doing that at scale is really hard. So maybe you just want the language model to say, these are the features I'm using, and the model doesn't have to do anything about them. They just need to surface them to a human.
But let's say you ask it and it tells you that it uses the gender.
Yeah.
That doesn't mean that you should not use the model.
Well, yes, yeah, exactly.
So what do you do with that? I guess that's the question.
So the doctor will just look at that and say, okay, this is a factor, or this is a factor to consider, or if not, then I don't trust this decision. If this is, then I still trust the model's decision, basically.
And going back to the question about evaluation, do you have a sense of how well the evaluation that you're doing does correlate with human? Like, have you done any human studies, or even qualitatively, do you have a sense from looking at examples of how well
It correlates with
it
human
correlates
judgments.
with human judgment?
Yeah, actually, a really interesting thing is we so going back to some of these features are kind of weird and hard to describe. So we actually looked at some of the error cases where the self-model was not explaining the feature correctly, and we actually found that in many cases the self-model was actually a lot more faithful than the noisy annotation procedure. So we did go in and do a little bit of human validation of some of these labels. But I would be super interested in running that kind of full end-to-end user experiment.
Gotcha. Any final burning questions? Okay, we're just about at time, so perfect timing. Thanks again.